Good morning, good evening, good day. Welcome to the Querying Best Practices for Azure Synapse Analytics session that I'll be delivering to you today as part of the Data Platform Summit 2020, a virtual conference. It's a pleasure for me to be delivering this to you, and it's a pre-recorded session, so I'm hoping that during this session, if you have any questions, etc., that you're putting them into the chat window and I can answer them with you online as well. So to start, my name is Charley Hanania. I'm a data platform MVP and I'm the CEO and data platform specialist at my own company called QS2 AG, Quality Software Solutions, based out of Switzerland. I'm an MCT regional lead, and I'm certified on most of the data platform capabilities within the Microsoft Cloud. And you can catch me at any time, connect with me on LinkedIn or on Twitter, as you can see on the contact details there. Feel free to contact us at any time. So the modern data warehousing and analytics estate. Now, when we thought about data warehouses before, we used to think about scalable relational database management systems, or OLAP cubes, and SSIS as the piping to manage transformations and data ingestion. Now with the capabilities available to us in the cloud, the data warehouse piece is redefined to be a central hub with spokes to other platform components, such as Azure Machine Learning, Power BI, the Azure Data Share capability, and other connected applications and services within the Microsoft Azure Cloud. To discuss more about how this all works and how it all fits together, I'm going to look at some of the general analytics pattern and the core concepts that are within the Synapse Analytics components themselves. So Synapse Analytics in and of itself is an integrated platform for BI, AI, and continuous intelligence. That's the marketing spiel. But it's designed to bring all the functions and features we need for big data and analytics within one workspace. From here, you can do such things as relational and structured querying and transformations on databases, data warehouses, or even using Spark. You can access files in batches and on the data lake. You can get streamed data from sources like Cosmos DB, Event Hubs, etc. And you can design pipelines using familiar data factory concepts and functions that you're used to within the Azure Fabric. On top of that, you can also build Power BI reports that leverage machine learning features, or pump your data into and get data from Azure Machine Learning services as well. This is all based on the Azure Data Lake storage as well there. And it follows the general pattern that we find within the transformation and analytics workloads, which is basically loading, storing, transforming, serving data within your analytical ecosystem. The Synapse Analytics service went into general availability late last year with a new user interface called Synapse Studio. Synapse Studio ties together the full breadth of the underlying capabilities into one workspace. The web-native experience ties data preparation, data management, data warehousing, big data and AI tasks together for data engineers such as myself, allowing us to do every task we need to build a complete solution in one location. The Studio workspace is deployed in a specific region, and it's under a resource group, and it's associated with Azure Data Lake storage account and a file system for storage of temporary data. Datasets, pipelines, and notebooks, dashboards, and pools can be created and managed within these panes that you can see here on the left, and which are described here as well, and can be shared across the team so that data engineering operations can be managed in similar fashion to what is done now within developer CI/CD workspaces through the integration with existing enterprise DevOps repositories and components like GitHub. The workspace itself allows you to perform analytics with SQL and Apache Spark, as we mentioned earlier. Resources available for SQL and Spark analytics are organized into SQL and Spark pools with two consumption models. These are dedicated and serverless. The dedicated SQL pool model uses provisioned SQL data warehouses. A workspace can have as many of these as you want. And the serverless model uses a stateless service, SQL data warehouse called SQL on Demand. As shown on this slide, SQL pools are best used as an optimized repository, which we're going to go into later for how we can do those optimizations for your loading and querying workloads. Whereas the on-demand capability is great for data exploration and for directly querying files over the data lake. SQL Serverless has no local storage. It only contains metadata objects that are stored in the database so that it can be spun up and down very quickly to enable ad hoc querying and business intelligence tools to tap into the data lake. Serverless isn't paid for by capacity as SQL pools are, but only for the time spent running the queries, which are charged at a per terabyte of data processed. Now, alongside these two is Apache Spark, and an Apache Spark pool can provide open source big data compute capabilities. After you've created an Apache Spark pool in your Synapse workspace, data can be loaded, modeled, and processed and distributed for faster analytical insight because it's generally really good for all the transformations and things you want to do. So on this slide, you can see here what the similarities are and what some of the key differences are in here as well. When we're talking about the architecture, I want to walk you through some of the key technical architecture components within the SQL pools. First and foremost is the control node. The control node is what we interact with when we're dealing with the Synapse Analytics SQL pool. The control node runs the MPP engine and optimizes queries for parallel processing, and then passes operations to the compute nodes to do their work in parallel. The compute nodes access all the user data in optimized Azure storage, and they run the parallel queries. The data movement service, or DMS, is a system-level internal service that moves data across the nodes as necessary to run queries in parallel and return accurate results. This massively parallel processing engine that I've just described is a clustered parallel scale-out compute architecture, and you find it now in a lot of the elastic cloud capability, data warehouse capabilities, and they're all bundled together in what's called the cluster. With the approach that is being used here, when it comes time to query and aggregate the data, each server inside the cluster gets assigned a chunk of the work, and all the servers perform the constituent portions of the queries simultaneously. This divide and conquer approach reduces the query time significantly, as you can imagine. On top of this, or below this per se, is the decoupled storage. Now, the decoupled storage is basically set up in what's called storage distributions. And a distribution is the basic unit of a storage for distributed data. The data is segmented into 60 parts, which are then stored in a compressed format. And so it's completely decoupled from the compute and the control nodes. When decoupled storage and compute, when using Synapse SQL pools, when doing that, we can basically independently size the compute power irrespective of our storage needs because we've got that standard 60 set of distributions. We can grow and shrink that compute as necessary within the SQL data warehouse without having to move any of the data. And we can pause and resume the compute capacity while leaving that data completely intact so that you only pay for the storage as it's stored and not for the compute while you've paused it. That way you've basically got the flexibility of starting and stopping or pausing and resuming your SQL pool infrastructure to cope with your operational hours and to save costs because it's not a cheap service per se when compared to Azure SQL DB, for example. So this holds true. This holds true when we're talking about loading data as well. So as you can see there, the control node receives the data, and then that sends it off to the compute nodes, which then process the data and queues it up and writes it then to the storage. Similarly, sorry, I've got a bit of a cold. Similarly, when you're reading data, we're basically reading off the disks in parallel, which doesn't seem, the animation seems to be not working. We read the data in parallel. It gets processed by the compute nodes and then sent to the control node. And then that's where we get access to it through our workloads. So once again, the compute nodes take the data from the storage in parallel, processes it in a queued fashion, and then sends it to the control node. Now, the parallelism and the queuing depends on how many of these compute nodes that you have. So then when a query hits Synapse, it firstly determines whether the query is in the results cache, and which is on the control node itself. And if it's not, then it basically pushes it down to the compute nodes and to the storage. If it is able to service it from the control nodes for the result cache, it's basically got the best response time. It's basically going to return the data set within about 200 milliseconds. Below on the compute nodes themselves, Synapse also has these in-memory and SSD caches within the compute nodes. And it's the same approach as what you find within Azure SQL Database or the on-premises product SQL Server. But then whenever you need to get that data, it basically sits within the buffer cache or the caching capability within SSD in memory until it needs it, and basically gets sent out as it does through a normal last in, first out sort of approach. Now, talking about concurrent workloads, we need to talk a bit more about the architecture, because we've spoken about how it's scaled and so forth, but it makes no sense to talk about scale without talking about concurrency. And it's actually a deficiency that a lot of the other platforms have, which is pretty well versed within Synapse Analytics. So let's take a look at how the compute pools or the SQL pools are sized. There are 16 performance levels, as they call it, or compute sizes within Synapse Analytics, SQL pools. If we take a look here, we've got the 100 to 500C, which basically has one node allocated to it, and it basically then distributes, it basically has to allocate those 60 storage distributions on that one compute node. So you've got a lot of queuing here, if you can imagine, happening on that one node to get to the data. The difference here between the different sizes is the memory assigned per gigabyte, and therefore the maximum number of queries that you can run concurrently. So for the 100C, you get 60 gigabytes worth of memory, which isn't too bad if you think about it. For 200C, it's double that, and therefore you have double the number of concurrent queries, because these are arranged in what are called slots, which we'll discuss in a couple of slides. As we go to the 300C, same compute number of nodes, which means the same distribution, but you now have more memory, which is triple, of course, the base level of 60 gigabytes to 180. And in that case, you can actually have 12 concurrent queries, and so on and so forth, until you get up to 20 concurrent queries with 300 gigabytes of memory. Okay. When you go one size larger, you basically get 2 compute nodes here for the 1000C. That then means that your distributions are halved, so you've got access to 30 distributions per node, storage distributions that is, and in this case you double again the amount of memory available, and you then have also more concurrent queries that are possible within there. If you go to 1500C, you get a third compute node, which then means that the 60 distributions are divided by 3, so you've got 20. And you've got more memory, and in this case, more concurrent, the same number of concurrent queries that you'd have. So consider using, for example, 1500 versus 1000. If you've got the same workload, but you want it to operate with higher memory utilization and more distributions per node, or less distributions per node. Take a look now at the rest of these, right? So we've got 2000C, 2500, all the way down to 30,000C. Basically, we start looking at the greater numbers of compute nodes, which means that the distributions get relatively smaller per compute node until we get up to the maximum of 60 compute nodes, which means that each compute node can query and write to a distribution in parallel. What that also means here is that we get more memory per compute node because they're assigned per compute node. And in this case, we also get more concurrent queries available to us, or more slots available to us to actually work off. Notice here that we have 48, 48, 64, 64, and the rest here are 128. So that's 128 concurrent queries that are possible within the SQL pool. So if you want to have more concurrent users, but you know that the workloads are lighter than they might be, you can actually go for the 5000C, sorry, the 6000C, and get the most number of concurrent queries for 3.6 terabytes of memory, and not too bad when we're talking about 5 distributions per compute node being queried, okay, and 12 compute nodes overall that are basically segmenting and segregating your data and processing those queries themselves. So these are some of the ideas that basically you need to take into account when you're querying, because you can scale and size your compute nodes as you go along. Noticing also, of course, that when you do that, you might lose connectivity as it basically scales and works up and or down the compute capacity. But keep that in mind when you're working on larger or high or low utilization times within your distributions and workloads. So let's take a second to look into now a concept called concurrency limits. SQL pools leverage this concept of what's called static and dynamic resource classes. Now, these resource classes are assigned in this sort of a way. You basically assign the role, which is the resource class, and the resource class can be assigned to a user. And that way you basically manage or limit how many queries can be run using that resource class. If we're looking at a large RC, which we'll see in a second, it basically limits the number of slots available to you to 16. And you've got basically from small to extra large. And again, as I mentioned before, you've got dynamic and static resource classes available. So let's take a look at a bit of an example here. So if we're using the 1000C resource data warehouse size, we would basically get 40 slots and have a maximum of 32 concurrent queries. How can that be used in any case? If we've got a number of different types of resource classes here, we've got small RC and a static resource class of 20, this one's dynamic and this one's static. The dynamic one, in this case, as a small one, uses one slot for each query, one slot here within it for each query, and the static would use 2 slots for the query. The medium would use 4, and the static RC50 would use 16. So as you can see here, as we're getting more queries into the system, we're using more slots and we're putting more load in terms of the concurrent queries. Whichever one of these gets hit first, that's where we basically stop in terms of the capabilities, and then queries start to queue up before they can start being processed. So here you can see you've still got more queries available, but because of the sizes that were chosen, or in this case, because of the sizes that were chosen for the resource classes, we used up most of those concurrency slots. And that's mainly focused on the amount of memory that you've got available to you. So the lower your resource class, the less memory you use per query, and then the more of these you could actually use. As you can see here with the blue one, 1, 2, 3, 4, 5, 6, 7, 8 were used, and you could actually have had more had you not had the static RC50, which in this case was only one of those queries, which took up the majority of the concurrency slots available to you. Similarly, when we want to look at these concurrency slots to basically expound on it a bit more and basically add more information to it, it's focused more on, again, on this memory, CPU, and I/O basic concurrency. And so the way that we basically allow multiple queries to run in parallel, we have to look at some sort of concurrency algorithm. Other platforms don't actually do this very well. A lot of the time you need to scale up your infrastructure to be able to have more concurrency, and it basically usually is a linear type of scale. Whereas in here we have the flexibility of assigning different workloads, different resource classes, so that you can determine internally how much you want to be running in parallel and how much queuing you want to run from that perspective as well. Let's take a look at something else that's been built in and is basically inherited from SQL Server and Azure SQL DB. So this capability that we're talking about now is the concept that we know and is tried and trusted called Resource Governor. It's not called Resource Governor here, it's called Workload Aware Query Execution or Workload Isolation. And the idea is basically you create a workload group and you set a maximum concurrency amount of resources to be assigned. In this case, we've got sales and marketing as the example. While sales and marketing workloads are running in parallel, we only want sales to take up a maximum of 60%. Okay. The cap in and of itself is 100. So if there's no marketing workload, we can allow it to take up the full 100%. And the maximum concurrency is 6. So we're only allowing 6 concurrent connections or workloads to happen through the sales connection. If there are no other workloads, the constraints are then lifted in this case, and we're brought up to the 100%. And then the sales workloads can basically utilize as much of the compute as necessary and memory as necessary to finish its querying workloads per se. On top of this, okay, in terms of query isolation, we now have something called query importance. Query importance is basically the idea that not all users or not all connections are created equal. As you can see here, you basically give an importance factor to the workload classifier. And within here, there's low, below normal, normal, above normal, and high. And these are basically escalations as we go forward. What happens here, as we mentioned before, that if you're running a set of queries, you're basically going to, once you've used up all of the slots available to you, you're going to have a set of queries that are queued. When you assign the importance to these different workloads, you can then say, well, this, by default, anything that's got a high workload or anything that's got a higher class assigned to it or importance assigned to it will fill up any of the empty slots as they complete faster. So in this case, slot 3 is completed or query 3 is completed, and the high workload of the CEO in this case jumped or skipped the line to get into the workload running group. These ones here are now queued, as you can see, and as you can imagine, we would have then 9 as the next workload that's being run, and then 11 as the next workload that's run, and then 10. So 9, 11, and 10 would be run from that perspective. So workload importance allows you to prioritize the workload group so that once an available slot is opened, you jump the queue per se to get in there. Pretty strong capability when you're trying to fine-tune your workloads per se. So let's take a look now at some of the other capabilities that we've got, apart from what's available within the infrastructure and the architecture, to be able to get better querying and optimize your querying workloads as well. So we've described previously that data used by SQL pools is sharded into a number of different distributions which are compressed by default. So to optimize the performance of the system, there are some alternative and supplementary capabilities and patterns that are created which are focused on MPP, which we wouldn't be able to find within a standard sort of SQL Server on-premises or Azure SQL database workload. So these sharding distributions are round-robin distributions, hash distributed tables, and replicated tables. Now, remember, I'll reiterate here. A distribution is the basic building block or unit of storage for processing and for parallel queries that run on distributed data. When SQL pools run a query, the work's divided into these 60 smaller queries that can be run in parallel on the compute nodes. Each of the 60 smaller queries runs on one of these data distributions. And each compute node manages one or more of these 60 distributions depending on the sizing that you actually assign to it. And the SQL pool can have a maximum, as you said, of one compute to one distribution, because there are 60 distributions, so you can have a maximum of 60 compute nodes. A SQL pool with the minimum compute resources has all the distributions, as we said before, on that one compute node. So all the rest are then queued, waiting to be archived. So in that case, we're talking about serial processing rather than parallel processing. And in this case now, we can tailor these sharding approaches with the knowledge of how our data is comprised. The way that we can further enhance the querying performance on the analytics platform is by discussing these three types of distributions in detail. First one here is round-robin distributions. Now, when we don't specify a table distribution in Azure Synapse Analytics, the table default is round-robin. A round-robin table is the simplest table to create and delivers the fastest performance when used as a staging tables or for loads. A round-robin distributed table distributes data evenly across the compute nodes without any further optimizations. It doesn't need to do any processing or lookups or anything like that. It basically chooses a distribution at random and then buffers the rows that are assigned to the distribution sequentially in chunks, and then keeps on working around until the data is complete for loads and for querying. It's quick to load data in a round-robin table, but keep in mind now that querying performance can often be better with the next one that we're going to be discussing, which is called hash distributed tables, because joins on the round-robin tables require a lot of reshuffling of the data to each of these compute nodes from the underlying storage, which then takes additional time. Imagine if it's been randomly pushed across, you might end up having to query all 60 distributions and then filter it in on one or two of these nodes, and then in serial in this case, and then once the data is complete, or the join or the filtering is complete, send that data back up to the main node here. So consider using round-robin distributions for the tables when you're getting started as a simple starting point when you want to take a look at the data, or at least start looking at putting the data in there, because it is the default. Use it also if you've got no obvious joining key between the different data sets, and if there isn't a good candidate column for hashing or distributing the data on a hash function per se. Consider it also if the data isn't so big and the optimization that you want to do is more in the compute rather than on the storage. So in that way, basically you need to weigh up whether you want to use more compute or push more data out and copy more data across. If it's smaller data sets, it shouldn't make too big of a deal, so you can still use round-robin distributions. In some of our testing for customers and on the TPC tests that we've done in the past, we found that the default round-robin distributions catered for 80–90% of the workloads without too much of a need to do any more optimizations. The other time that you'd want to be using it, as I said before, is when you're creating temporary staging tables. So you're loading data off the data lake, and then you want to push that out into optimized distributions within the database itself. So consider this in most cases as the default, and from there you'll then look at what other optimizations you can do from a distribution perspective, and you can then apply those same distributions on the indexing capabilities that we're going to discuss in a few slides as well. It's great also when we're talking about data tables of any size. So consider it, because it's doing things in chunks, it's just pushing that data across your nodes as necessary, and so from that perspective it's balancing it out pretty evenly as well. So the second one here is hash distributions. As you can see from the FX here, a hash distributed table can actually deliver the highest performance if you know your data and if you hash on the right column, especially when we're talking about very large tables. Okay, Now, to shard data into a hash distributed table, SQL Pools uses a hash function or algorithm to deterministically assign each row into one of these distributions. In the table definition, one of the columns is designated as the distribution column. And so the hash function uses the values that come out of there to distribute that column throughout the system. So what you're trying to do is trying to keep the data together that makes sense to be kept together, especially when you're talking about the querying workloads. So when do you find that there's a lot of data that's similar or that can be bunched together? In data warehousing, these are generally when we're talking about fact tables. So start looking at these when you're looking into queries that are run against large fact tables that might be within a star schema or less optimally within a snowflake schema per se. And try to consider them when you don't have too much of a data skew within the distribution values. So what that means is basically if, for example, this one is much larger and the data is skewed towards this one here, the queries aren't going to be able to come back if you're querying across the whole data set until this workload has completed. So even if this one and this one complete very, very quickly, we still need to wait for the data that's distributed here to complete before we can send it up to the core node. So as a starting point, use them on tables that are greater than 2 gigabytes in size, because that's when you start to find the enhancements that are within the platform starting to take shape. And look at it from look at it for tables that are getting a lot of inserts, because then that gets funneled directly into the right distribution as we go forward, or updates as well. But make sure you're not updating the distribution column that you want to use for the deterministic algorithms. Last one we're going to discuss here is replicated tables from a distribution perspective. Replicated tables basically is a way to provide really fast query performance for small tables. So in general, that means we're doing this for dimension tables. And the table that's replicated basically is a full copy of that table that's distributed across each of the compute nodes. Replicating a table removes the need for transferring that data among the compute nodes for joining or aggregating the data, because now that data is local. So if you're filtering, you can filter directly to that table as if you're running all your data off one compute node and one storage allocation. Consider using replicated distributions for tables when you have dimension tables that are in a star schema that are less than 2 gigabytes in size, because remember, you're pushing these data sets across all of the nodes, and each time you distribute that, you're creating a copy of this same table within your storage subsystem because it is completely separate. And think about it when also you're not updating that data on a regular basis, because then you might invalidate the cache. So basically, when this is in cache or copied to each of the different nodes, you may find that after you've updated enough of that data within the replicated table, the table itself gets invalidated and needs to take a copy again and redistribute it next time you query that table. What that means is that during the time that you're running that query, the SQL pool needs to take the time to take the data from where it's stored natively and then distribute it across as a new version. So that's where you might find some impact when you're basically querying it. And you might also need to consider that when you're scaling or spinning up your compute node for the first time, your SQL pool for the first time, that you need to usually select top 1%, for example, or top 1 of the table will actually trigger the distribution of that table for replication across the different compute nodes. Keep in mind from that perspective, this last statement here, where it must be re-replicated because it gets invalidated after your SQL pool is scaled. Consider what that means. If I scale this from 4 compute nodes to 6, okay, through basically the data warehouse unit sizing, this has to be invalidated, and then that table that's being replicated has to be pushed across all 6 as its current version. So now let's take a look at some of the indexing strategies that we've all come to love from SQL Server and Azure SQL Database as a relational database management system. And most of the enhancements that we are finding here that we have grown used to within the core data platform that we generally use are also implemented here, with a couple of exceptions to that list. For example, we've got this heap table concept. You know what a heap table is? A heap table is a table that doesn't have a column, a clustered index on it, be it column store or row store type. So what that means is that by default, as we already discussed from a distribution perspective, it will use round robin. Also by default, we're creating clustered column store indexes on each of the tables that gets loaded into the system. This allows us then to compress using the compute and to write minimal data to the optimized storage. Okay, and that way the compute can be leveraged time and time again to encode and decode the data, so that when you're working with it, you're really minimizing the traffic, the data traffic going through the system. And that's generally the pain point for any sort of distributed data or even non-distributed data platform. So if you take this off, if you want to use a heaped table, or basically no column store index on top of that, no clustered index on top of that, you're basically using heaps. It might be, well, you need a test, of course, but you might find that it's faster for writing, because you're then not doing any sort of compression algorithms and so forth within compute. If you're finding that you're using a lot of compute using that time, and you would rather offload that workload onto the storage. But in general, it's going to be very poor performing when you're querying that data. So as we're talking about querying in this case, heap tables generally wouldn't be a recommendation, but it is a capability within the system per se. The second one here is the clustered column store index, which, as I mentioned, is the default. And consider using on top of this the option of column store archive. Now, if you haven't used column store archive in the past, even on the on-premises workloads, consider that if you get, say, on average, a 90% reduction in size using column store, depending on how you've distributed your data and sequenced your data per se, you may get an additional 30% saving if you used column store archive as an option on your column store index. Now, considering we're talking MPP scale out architectures with lots of compute nodes, with lots of memory and compute capabilities, using the column store underscore archive hint or option means that you're further reducing the size of the data that you're writing to Azure Blob Storage. Okay, so yeah, you need to decide or test for yourself where you might get performance improvements from that perspective. And it usually helps when you've got a lot of similar data sets running in order from the column perspective. What we also have here is clustered row store indexes. So that's the normal clustered index that we've grown to love and is the default when we're talking relational database servers, database systems. But these, of course, as you can only have one clustered index on a table, these are mutually exclusive. You can't have a clustered column store index and a clustered row store index on top of it. But what you can have is one of these two types of clustered indexes and a non-clustered row store index. Consider when you would use these two. Clustered indexes are generally used for when you're doing range queries or table scans or range scans, and non-clustered row store indexes are used for lookups, specific lookups, or when you're trying to filter on a specific row per se, or set of rows per se. So this way you can leverage both of those capabilities within your already scaled out and distributed system within the SQL pools to be able to minimize the amount of traffic that's going between the nodes and into the core node itself. On top of this also, you've probably also used the table partition capabilities. Table partitions are horizontally partitioning your tables, especially for large fact tables, where you want to basically segregate your data into, for example, if we're talking about a time series fact table, you want to maybe distribute it into day or month or year, whatever it might be. And that way you get better compression, better statistics on those partitions. And the way that Synapse Analytics works is that it can then also filter down to the specific partition that's needed if you've got the right query or filtering mechanisms in place. So it doesn't have to do a full scan of the table. It can just go and isolate that partition and bring back the data that you need. This then affects us from when we talk about statistics. Now, table partitions or partitioning your table allows us then to have better statistics on that segment of horizontal data, of that data set. And we always want better statistics, because that allows the query optimizer that runs in an MPP scale-out fashion to better decide what to do and how to get that data to you as quickly as possible. On top of that also, if we think about statistics and partitions, are the concept of views. Now, we already know what views are, and we've probably already used materialized views if you're on Enterprise Edition, for example, on premises, or if you're using Azure SQL Database. And materialized views are the capability of putting a clustered index on top of a view. What that does is basically it stores the data that is resulting from the query itself, and it then stores the data and updates the data in line whenever you're loading or changing that data. So whenever you query a materialized view, or whenever you have a query that can be processed using materialized view, it looks first to see whether it can be, well, it'll decide per se what's better, to use the base table and distributions, or the materialized view with the distributions associated with it as well. And the statistics then that are created on top of the index that are on top of there. So the key discussion here for all of these types of indexes and strategies is statistics. So to improve your query performance, it's always preferred to create statistics on not only the columns that you're using for lookups and joins, but on all the columns of the tables, especially after the first load, because you don't want the statistics being updated during a load, or when substantial changes are occurring to the data itself. Now, this can be done manually, so you can run and update statistics, or you can enable auto-create statistics on the database itself or on the data warehouse itself, so that it can manage that on its own depending on how much the data is changing itself. So keep that in mind. It's the same sort of thing that you'd be talking about from a statistics perspective when you're talking about any query-intensive workloads on premises or in the cloud on the SQL Server platform stack. What we don't have yet, and I say yet because I don't know whether it will be in the future, but it's definitely a good way to enhance your performance on premises or within your general database workloads, is filtered indexes. Filtered indexes is basically an index with a where clause. So that allows you then to really have a small set of indexes that are focused on returning back the data that you want, or the data that you want to filter against. And what isn't available yet, and I don't know when, if it will be as well, are non-clustered column store indexes that can be used in conjunction with these clustered column store or clustered row store indexes for compressed lookups as well. So now we've come to the end of this presentation. I hope you've enjoyed it. I've certainly enjoyed presenting to you, even though I've got a cold or the flu. I hope I wasn't that difficult to understand. But thanks for attending, and I hope you're getting a lot out of the Data Platform Summit itself. And I hope that you've been asking all the queries and questions that you've got within the chat, and I'm more than happy to discuss these with you within the community area or on this chat as we go further on. So thank you very much for attending and have a great day.